All right, looks like we've hit an endpoint, at least for now. So I will go ahead and welcome you all to this week's edition of eoPERCS, where we will have Mike MacFerrin from the University of Colorado Boulder give a talk titled Emerging Hydrologic Feedbacks on the Greenland Ice Sheet, What a Rapidly Changing Climate is Revealing About the Ice Sheet's Future and Past. But before we get to Mike, we have just a few little logistical things that I'll go through to introduce you all to our seminar. So the format for today's seminar, if you've been to other eoPERCS, will be very similar. We'll start with this welcome and announcements. Then Mike will give his talk, and we'll have some time for questions and answers following the talk. And then Mike has agreed to stick around for tea time, so we welcome you all to join us for a few minutes after the talk as well to chat with Mike. So during your talk, or during Mike's talk, please don't forget to send your questions via the chat to the questions at eoPERCS host, who this week is Raymond. So just some reminders, eoPERCS values the participation of everyone interested in the paleo sciences. So please remember to abide by the code of conduct that you agreed to during today's seminar. If you found yourself with a link without agreeing to the code of conduct, you can take a look at it on our website and also sign up for yourself so you can get the links each week. You should be muted. Please keep yourself muted for the duration of the talk. Again, you can ask questions by sending a chat to the questions at eoPERCS host, or after the talk by using the raise hand function, and we will unmute you at that point if you want to ask your question out loud. Additionally, if you have any technical issues during the talk, please send those to Raymond as well at the questions at eoPERCS host. We now have closed captions built into Zoom. You should be able to click the CC button in your Zoom controls to show or hide them and get the subtitles at the bottom of the screen if that's something that would help you. Additionally, we're always looking for nominations for outstanding early career researchers. We'll drop the link where you can nominate people that you'd like to see give a talk in the chat. And we'll also drop a link in the chat for our weekly feedback form that just collects demographic information. It's anonymous and optional, but encouraged. And again, we'll drop those into the chat, or Raymond's already done it probably. So want to welcome our speaker for today, Mike MacFerrin. Mike got a bachelor's at the University of Michigan before going on and getting a master's and PhD at the University of Colorado Boulder, and is currently there working as a research scientist. And Mike's going to talk to us today about the Greenland Ice Sheet and sort of what paleo people can do to help out with some of the stuff we're trying to figure out there. So thank you very much for agreeing to give a talk, Mike. If you want to go ahead and take over the screen share, we can get started with the actually interesting part.
All right. Thank you. And thank you for everyone. This is pretty exciting. So in full honesty, I, by most measures, am not much of a paleo person. Most of what I do is modern day remote sensing and field studies on the ice sheet. But what I'm really wanting to go over today is some of it's going to be a bit of a review about the way that our understanding of ice sheet hydrology, the way that meltwater in particular is working on the ice sheets, has been dramatically reformed multiple times just in the last 10 years. And in fact, it's still changing now. I was watching presentations at the last AGU meeting, American Geophysical Union meeting, where like some of the latest results we've got are being questioned and upended, and in some really exciting ways. So, but this presents a lot of challenges for the paleo community. So I want to kind of go in a little bit and first start. Oh, let me get to where with paleo evidence. So obviously, the biggest way or one of the most prominent ways, I should say, that we get paleo data from the ice sheets is through ice core records. It's obviously well known. You can get all sorts of measurements, atmospheric and otherwise. And if you can get to the bed of the ice sheet, which not all ice cores do, but a number of them do, they can actually dull their drill at the very end by drilling straight through the bedrock and pulling up what they can. You can actually tell a lot about what happened when the ice sheet wasn't there last, or when the ice sheet originally came to be in that location. It's only a point location, but it tells us the best we can tell. And the very first core to the ice sheet, or core through the ice sheet to the bed, was actually at Camp Century, Greenland in 1963 that came out. And the Camp Century core is still cited today. So we since have many other cores of higher quality, but there's something significant about the very first core to the bed of an ice sheet. And a really curious thing was that the sediments that they collected at the bottom of the ice sheet, so it wasn't bare bedrock there. It was a little pocket where sediments have been trapped under the ice. And they pulled up several meters of sediment, some of which literally sat in a freezer for more than 50 years. And just recently, in a paper last fall, they pulled some of this sediment out and really analyzed it, and found that over at least the last couple million years, that the ice sheet at Camp Century has been exposed, had 2 episodes of ice-free vegetated conditions. So there was tundra there or other vegetation, which represents, I mean, there's currently 1,368 meters of ice at Camp Century. So that's a pretty significant drawdown of the ice. And we know from modeling that it is possible to make the ice sheet disappear. There was a recent paper a couple of years ago by Andy Ashwindon that modeled out under different climate scenarios out to the year 3000. So this was a long range model that, especially if you take the worst case scenarios, this is the RCP 8.5, the burn everything we can dig up sort of scenario by the end of the century, and then just keep that going through the year 3000, that you can make most of the ice sheet disappear by the year 3000. This is a model that handles both dynamics and surface mass balance, that surface melt and snowfall. But this RCP 8.5 forcing is a much larger forcing than anything that has happened in the last couple of million years. And so if you look at the paleo evidence, it's something closer what's happened in the last couple million years, where at least at Camp Century, which is around here, has been ice-free on multiple occasions. It's something closer to about RCP 4.5, or it's something around that if you project it out. And what that tells us is we may be underestimating the rates at which you can make the Greenland ice sheet disappear. We know that Antarctica, at least West Antarctica, is subject to potential rapid collapse, and it's being argued right now that is likely underway at the moment, the beginnings of it. That's due to the geometry of the bedrock in Antarctica. Greenland doesn't have that level of vulnerability that West Antarctica does, but yet we see evidence from cores in multiple locations that it's been ice-free multiple times in the past. And so our understanding of, I mean, this is obviously one of the reasons why paleo evidence is so valuable, to show us under past forcings what happened to the ice. So there's a bit of a gap there that we may be missing some feedbacks. And what I'm open to go into is a bit of an evolution of our understanding of ice sheet hydrology. So the ways that meltwater, because meltwater runoff is actually, meltwater runoff is actually one of the largest ways that Greenland loses mass today. Unlike Antarctica, where it's almost all icebergs calving off in dynamics, the ice movement in Greenland, at least half, if not more, of the mass loss is just runoff, just melt straight off the ice sheet. Not all of it goes straight off the ice sheet. That's what I'm going to be talking about in a bit. But our understanding of ice sheet hydrology really took a big leap forward in the 60s. During the Cold War, the US military had a large set of operations in Greenland, including several large traverses that mapped out these different, what we call facies of the ice sheet. So down low where it's warm, it melts down to bare ice every year. This is called the runoff zone, also called the ablation zone. And then you get into the accumulation zone, all these facies up high, where up at the top, it's pretty much dry snow. It doesn't melt. This would be at places like Summit, Greenland, and then, but there's a vast region in between that's we call the percolation or wet snow facies, where some meltwater percolates into the snow and then refreezes into all these little ice lenses. It hits these hydrologic little local barriers and spreads out, pipes down and freezes into all these little melt layers. This was back in the days when you could have a couple hundred people working on a project for 4 years. This was a 4-year traverse of multiple cores and huge snow pits and have one author on the paper. These days, it's kind of the opposite. You get one person doing most of the work and 13 authors on the paper. But they mapped out the best guess. Of course, they didn't map the entire ice sheet. Most of their traverse was coming from Northwest Greenland up through Summit and then down here. But the best of their ability, they mapped out these facies of the Greenland ice sheet. And this is literally Xeroxed in from a 1962 report. So apologies if it's a little hard to see. But overall, this is pretty much a fairly accurate representation of where, at least up until recently, these facies existed, except they didn't quite get it all. There's some stuff going on they didn't know about. In 2011, I had the benefit of being at an AGU talk where Rick Forster was pulling up evidence. They'd just been on a traverse earlier that year in March, late March. So this is late winter on the Greenland ice sheet. And in Southeast Greenland, once they got about 10 meters down, they were pulling up fern cores. They were pulling up liquid water. It's -20 out. That water, it's been cold all winter. That water should not be there. And what they really discovered is that there's aquifers in the fern. In places where you have really high accumulation rates, you actually get water that stays liquid inside the underneath the surface of the ice sheet. And it snows so much that it accumulates and insulates all that water. You need a lot of melt and a lot of accumulation in order to generate these things. But they managed to then take radar from NASA's Operation Icebridge. This is an airborne mission that had been flying for several years already, and we're able to map out in the radar where these things show up. So radar signals if they penetrate through dry snow and ice, but then will reflect very brightly off of liquid water that's in the fern. So using all these flight lines, they could map out areas where there's water in the ice sheet. And this isn't something that Benson ever knew existed. They simply hadn't traversed where these things exist. In the rest of the ice sheet, you'll notice that the fern aquifers do sort of they surround a little perimeter of parts of the ice sheet where there's very high accumulation rates, but most of the ice sheet, the fern way up high here is not full of these aquifers, based so far as we can tell. And so a question is, with all this fern pore space, and by the way, when I talk about fern, what I'm talking about is old snow that's more than a year old, snow that accumulates year after year after year, slowly compresses into glacial ice. By the time it hits pore close-off density, that's when we call it solid ice, even if it's got some bubbles in it. But everything in between is fern. And fern can sit there for 100 years or more before being compressed into glacial ice. So there's a lot of pore space in the fern. And in 2012, Joel Harper and colleagues wrote a paper. They had done a traverse in Southwest Greenland and showed that there's a lot of pore space in the fern, which we already knew that, but they also showed that meltwater can, when you get large melt events, can actually get quite deep. They had tracked using temperature thermistor strings down into the snow and ice, tracked meltwater getting far deeper than percolating far deeper than they thought it would, below 10 meters depth. And so they surmised that even if you get a lot of meltwater up high, this fern is going to do a lot of absorbing. You've got fern that's 50 or more meters thick. That's a lot of pore space in there that can fill with meltwater. And so if you assume that all that meltwater could fill up, it could take decades. They find that decades are required even with more melting, even under the worst case scenarios, under a range of plausible future climate conditions, even the worst case ones, it's going to take decades to fill up this pore space before you could actually start getting runoff from higher in the ice sheet. And so this paper made it in Nature. It was basically saying, like, people are talking about, oh, runoff's getting higher and higher and higher. And they're like, whoop, there's a check on that. Once you get into the fern, it's just going to absorb. It's going to be a big sponge for decades until anything starts to run off there. Which, from a humanities perspective is fairly encouraging. All right, the ice sheet's got a buffer in it. About 6 months after I'd seen that talk, I was a new PhD student at University of Colorado. I was at my first campaign on the ice sheet. We were at Canyu, a spot of ice in far southwest Greenland, in the accumulation zone. On the surface, it seems kind of boring. You can look behind me in that image. It's nothing but flat white snow as far as the eye can see. We're a couple 100 kilometers from the nearest rock, except straight down. We're standing on about 2 kilometers of ice. But we were drilling fern cores, these shallow cores, to get records of recent melt there. So to measure these melt lenses that show up in the fern. And this is what we expected to find, is a bunch of these. We knew there'd been some big melt seasons here that had refrozen lenses like this into the cores. This is the kind of thing we pick up, and we measure the density and stratigraphy of these cores to get ideas of the recent melt history at this site. But after we got just a meter or two down, we started hitting core after core after core of solid ice. Just no real fern pore space, just solid ice. And we drilled straight through about 5 meters of solid ice before starting to hit patchy fern again. And we did this multiple locations around the camp. And within a whole kilometer span, everywhere we saw these 5 meter thick layers of ice. And we're like, holy crap, that's a lot of ice. And we were sitting around camp. This is on an absurdly warm day, waiting for a plane to pick us up. And wondering, like, well, with this much ice under our feet, solid ice, I mean, it doesn't seem like it'd take too long before the water would have nowhere to go. Like there's at least immediately under our feet, there's not a lot of pore space left. There's pore space under that for probably another 40, 50 meters. But how many more melt years would it take until the water just couldn't go anywhere and start running off again? Well, it took one. That summer in Greenland, 2012, this was just 2 months after we were there, Greenland had its largest melt event in recorded history, where at least on one day, the entire ice sheet, up to 98% of the ice sheet, was melting at once. It was the first time Summit Camp had melted in 160 years. And then it melted again later that month at Summit. That's this little tick mark right there. And Greenland had, and just the extent of melt isn't the hugest story here as far as I'm concerned. It's actually the degree of melt. There was this huge high pressure system parked over the Greenland ice sheet that just had incredibly warm temperatures from the south. That's and keep in mind, in Greenland summer, the sun never sets. So if you get a hot day, it can be a hot day that lasts 3-4 weeks. And at Canyu, looking at satellite images here from Landsat 7, we see runoff, slush fields forming right around our camp and running off to the west. So our answer of how many more years would it take until this area could start running off, we got an answer to pretty quick. And all that runoff this was far higher, by the way, than anybody had seen runoff in Southwest Greenland. Canyu had never run off before. It wasn't supposed to. In fact, Canyu is the upper Kangerlussuaq station, where this kind of thing isn't supposed to happen. They had Can M and Can L, medium and lower stations, to monitor the melt and runoff zones. This was the upper station where it's boring. And as things were running off up high here, this is from July 16th, it was going kind of crazy downhill. This is in May, when waters are low before the melt season's really kicked in much. This is the Watson River that the Russell Glacier, where we were at Canyu, feeds into this glacier, the runoff. This is in May when the water's low. But in July that year, this is what was happening. It was washing out the bridges. You're right there. It was flooding a tractor off the bridge. Sorry, the video quality isn't very good. And they never did find that tractor. No one was in it, thankfully. But that bridge had been there for 50 years and water never touched it. They had incredible melting, incredible amounts of runoff. And what we found was happening here, up in the dry snow zone of the ice. So this is like up at Summit Camp. You basically get snow in the winter. It warms up in the summer, doesn't really get hot enough to melt, but the snow slowly compresses down into glacial ice. That's the dry snow zone. Down in the ablation zone, this is down where it melts down to blue bare ice every year. You still get snow in the winter. It gets hot enough in the summer to melt all the snow away and then some of the ice, and the water runs off. And this feeds the rivers and lakes around Greenland. Happens every year. The biggest region of the ice sheet is in the middle, the percolation zone. This is where we were at CanU. You get snow in the winter. Again, it's cold everywhere there in the winter. And then but in the summer, it partially melts away and into these little ice lenses that get scattered in the fern column. And then the next year, you get snow on top of that. And the problem is when you start increasing the amount of melt, you start melting away more of that snow, you get more and more ice lenses in the top. And then pretty soon, after a number of years, you get these start to anneal together. So they freeze together and you get these solid, thick layers of ice that then become largely impermeable to future melt. So you get another warm summer and you get what we had at CanU, where water's literally just capped off and running right over the top of this, straight downhill. And you get areas of ice that are now feeding the rivers and the oceans around Greenland that didn't used to. And it's a way for runoff to sort of rapidly advance uphill. We had managed to do a campaign in 2013, the following summer after this big melt event, to map out these ice lenses, which I've since called ice slabs. And we're able to link it up with airborne radar from NASA's Operation Icebridge. It's the same mission that mapped out those aquifers, to tell everywhere in Greenland that we could find these ice slabs. And anywhere from 1 meter thick to 16 meters thick. Lakes form all over the top of these things, and get a pretty good map of where these things show up in Greenland. We know that lakes form atop them. We know they enhance runoff in really warm years. It's quite a large area. It's already at least 5% of the ice sheet that's covered in these things, and we'd only just discovered them. They've really only been there the last 20 years. We did some modeling showing the formation up through today and then out to 2100 under different climate scenarios. How big could these things get in the future? So using different models, this is RCP 4.5, sort of the moderate emissions, like if we met the Paris goals kind of emissions pathways, how big would these things get? But then the RCP 8.5, the burn baby burn scenario, by 2100 these things, especially under the most sensitive models, really expand dramatically into areas. I mean, this is up near the ice divide here, or even over the ice divide where you just capped it off. This is a scary ice sheet. And that contributes up to like an extra 6-7 centimeters to sea level rise beyond what Greenland was already going to do. This is runoff that wasn't really modeled. And talking about those aquifers, when you put these two things together, the ice slabs and aquifers, and then model both of those out to 2100, under different models here, so this is one of the, under RCP 8.5, a worst case scenario, but one of the least sensitive models and one of the most sensitive models, you really get an ice sheet that is far wetter than it ever used to be. This to me is a very scary picture. This one on the right. It's not saying it's going to go this way. We may not follow RCP 8.5, although right now, due to Arctic amplification and atmospheric feedbacks happening in Greenland that aren't yet fully captured by climate models, we are actually following, in terms of runoff in Greenland, the RCP 8.5 pathway closer than any other. This is a scary ice sheet. This is a wet, sloppy ice sheet that we don't know all the feedbacks there that happen in something like this. And these extreme melt events are getting more likely. 2012 was a big one, hadn't melted at Summit Camp before. Summit Camp melted briefly in 2019 again. Wasn't quite 100% of the ice sheet this time, but it was over 60% of the ice sheet melted. And again in 2021, we got it. Now keep in mind, Greenland the summit of Greenland had not melted. Now, this case didn't get quite to summit, but it did get very, very high. But summit hadn't melted in 160 years before 2012. Based just on weather station trends, Dan McGrath had a paper out in 2013 showing that if trends continue, the dry snow facies of the Greenland ice sheet will inevitably transition to a percolation facies. And there's a 50% probability of this transition occurring by 2025. That's 3 years from now. Now, his paper was in 2013 based on weather station data up through 2011. So this was 10 years ago, he was predicting this. And he defined percolation facies where melt happens at least once every other year. And we're kind of on track for that right now. It's hard to say by 2025. If it melts at summit camp again before 2025, from now, 2022, 23, 24, 25, we'll pretty much have hit that, where Greenland doesn't really have a dry snow zone anymore. To an ice sheet hydrologist, that's a major change just in the last 10, 15, 20 years. To turn a cold-based interior of the ice sheet into a percolation zone. And when I say cold-based, I'm actually talking about the bed as well, but I'll get to that in just a minute. One of the things we discovered while we were doing this work at CanU, this is a worldview image, one of these half-meter resolution images, sort of pixelated and zoomed out, but showing that 2012 runoff at CanU. This is actually after a brief snow event. You still see all the rivers, but they're a little covered in a dusting of snow. But one of the things that really shocked me when I zoomed in on these pictures is that you see all these little lines. And the first thing when I saw these lines is I'm like, it's got to be like an image artifact. But no, when I zoom in on other parts in these slush fields, you even see these lines filled with water. These are cracks in the snow. Now, keep in mind, the ice at CanU, it moves pretty slow. It's on the order of 50 to 55 meters a year. That's not very fast. It's 15, 20 centimeters a day. CanU isn't meant to be interesting, dynamic ice. It's slow, boring ice. That's what it's supposed to be. And it doesn't really move fast enough for crevasses to show up. Kristen Pointer had a 2015 paper out showing that crevasses shouldn't happen above 1,600 meters. Looking at the strain rates, the gradient in flow velocities, they found that the upper limit to where crevasses and therefore moulins are likely to form is 1,600 meters. Moulins is when water can flow to the bed of the ice sheet, usually starting at a crevasse. And just because the ice is so slow in the interior that it really shouldn't form cracks. But we were at CanU at 1,800 meters, where clearly there's cracks. There shouldn't be there. CanU's at 1,860 meters elevation. So we've already gotten above that. And why do we care? And actually, I had a student, an undergrad, actually go through that whole worldview image and mapped out hundreds of crevasses. This was time spent in ArcGIS digitizing lines, listening to a podcast. But it wasn't just, we had put some GPS stations to monitor these things, but there's a lot of cracks up there. And we strongly suspect that this is due to these ice slabs. The ice slabs still flowing over undulating terrain can crack up. And the problem is when you get these cracks right near lakes, because of the concept of hydrofracture. So when water fills a crack on the ice sheet, if it's a narrow, thin crack, as most beginning cracks are, water is heavier than ice. And the hydraulic head, the weight of this water pressing down against the walls of this crack are actually stronger than the overburden pressure of the ice pushing against it, which forces the crack open further. And then it gets even deeper, which forces the crack open further. You can actually, when you get enough water in a lake up top, if it can enter a crevasse, it can hydrofracture its way straight down through an arbitrary thickness of ice, 2 kilometers or more, straight to the bed. This is called hydrofracture. It happens. We see rapid lake drainages, lakes that are 5 kilometers across, drain in the span of 90 minutes once they've reached a conduit to the bed. And this does interesting things to ice sheet hydrology. There was and I've got the papers to all this sort of lit review here. If folks want to go through the slides or recording later, you can look these references up if you want. One of the big fears, what this does in 2002, there's a paper out that showed that when rapid lake drainages are happening, that it actually lubricates the bed of the ice and can speed up the ice. That it's taking ice that was sitting firmly on the bed before, now sticking a bunch of water under it. And we've actually seen from GPS measurements when there's a huge melt event in 2012, Russell Glacier, literally under 1.5 kilometers of ice, lifted up by 19 centimeters. It floated. And so you can lubricate the bed, which obviously can make it flow faster. So this is a link between surface hydrology and ice dynamics. Now, it's not that simple, actually. There's since been follow-up work that's shown that, yes, in warm melt years, it does in fact speed up the ice initially, but then once you get these drainage channels underneath the ice, they actually, in really warm years, form pretty quickly where it can efficiently drain the ice. That lift up, that hydraulic pressure is alleviated, the ice sits back down, but then after that, it actually slows down beyond the background rate, even slower than it was before. And in cooler years, when you only get a little bit of meltwater to the bed, not quite these huge injections, you actually get more ice dynamics speed up, sustained over the year than you do in the warm years. It's basically the area under this curve is actually larger in the cool years, which basically is indicating that the net effect of this effect is negligible or possibly even negative over a number of these outlet glaciers. Keep in mind, most of the folks that study ice dynamics in outlet glaciers are looking at the low elevation outlet glaciers here. This is ice that's anywhere from 0 to 1,000 meters thick, which is thick, mind you, but most of the ice sheet is 2,000 or more meters thick. And they don't really pay attention to that because that's the slow boring ice way up high where those guys drilling fern cores work. Modeling and some observations have shown that when you drain lakes high up on the ice due to added pressure, so there's more pressure at the base of the ice sheet, these big tunnels and surface, these basal channels don't really form. And when they do, they close quickly. They literally just, the pressure closes them very quickly. It's much higher pressure, much thicker ice, that when you get big injections of meltwater into a place where there's not a well-developed hydrologic system at the bed of the ice, that it can actually, large injections of meltwater can dominate over the entire summer in higher parts of the ablation region, especially in areas where there perhaps was a previously frozen bed. You get meltwater down there, there is no hydrologic system under the ice, and suddenly you create one. This can have a big effect. And we know that lakes are draining at higher and higher elevations. They're draining more often. This was a paper by Sarah Cooley when observation bias is addressed. They had been addressing the intermittency in satellite observations, and that causes a bias. Lakes above 16 meters are as likely to drain rapidly as lakes at lower elevations. And this is sort of consistent with us finding a whole bunch of cracks up there. Like, yes, they can in fact drain lakes way up high. This is kind of scary. Most of the ice in Greenland is thick. All right, this is a thickness map from the Bed Machine product. I didn't put the link to it in here, but showing most around the edges, this purple zone is from 0 to 1,500 meters thick. The vast majority of the ice is 1,500 or more meters thick, and most of the ice is slow. The ice dynamics modelers love to focus on these red hot or these yellow hot outlet glaciers. These are the really fast ice. This is Jakobshavn here, and Petermann Glacier up here, and Helheim down here, and Zachariah up here. These are the really big fast glaciers in Greenland, but most of it's this slow, boring ice. In fact, if I do a zoom on ice that's greater than 1,500 meters thick and moves at less than 100 meters a year, it's 56% of the ice area in Greenland, and it's over 84% of the ice volume. Most of the ice in Greenland is big, slow, boring ice. But we're draining lakes to the bed there now. Not all the way up to Summit Camp. Don't have any lakes there yet. Haven't formed any ice slabs there. But this is kind of scary. Now I'm actually close to reaching the limit about what we know. I've tried to measure the ice velocities, taking the time series of these velocity maps and see in the accumulation zone. This is this thick ice above 1,500 meters. Are we seeing an increase in ice velocities there yet? And so far, it's inconclusive. It turns out it's actually, this looks like a really clean picture here, but it's actually really hard to measure velocities way up high in the ice where it's flat white snow everywhere and there's no features you can really track. There's not like crevasses that you can see moving everywhere, big crevasses or big other features in the ice. It's just snow everywhere. And the error bars, what you're not seeing is the error bars are really huge here. So I did detect that there is a speed up, but it wasn't statistically significant. The errors on the measurements, especially early in the record in the 80s and 90s, are too big to really tell if things have sped up. We don't know yet. This takes more study to see if this is already kicking into gear. But what we're doing, best I can hypothesize, is this fat, slow ice in the interior. We're poking it. We're poking it hard, and we don't yet know how it's all going to react. If you get that map of runoff zones and ice slabs all the way up to, covering the entirety of South Greenland here, and aquifers, which can also drain into crevasses. There's papers showing that. What this is going to do to the ice dynamics. How fast could you collapse the Greenland ice sheet? We don't know yet. This blue area, this boring ice, this is where basal meltwater has the most impact. And so taking it back to the core record, there's unfortunately exists very little evidence of the hydrologic past of the ice sheet. The Greenland ice sheet and Antarctica, for that matter, do a really good job of literally scraping away most of the evidence of what's happened there before. We get these point records from cores, but those are just point records. Like, we don't have measurements over the whole ice sheet of the hydrologic past. We can't tell when the last time, in an area where there's a frozen bed, when the last time water was there. That's a difficult thing to tell. This is really me bringing up challenges to the paleo community. If we want to understand the history, we got to look at the warming events of the past. I don't have to explain this to a paleo community. This is what y'all do. But this really, there's big questions on feedbacks happening right now that our understanding is still evolving on these hydrologic feedbacks, that we're seeing it play out in real time. It's been kind of a wild ride in the last 10 years to be an ice sheet hydrologist in Greenland. There's new papers coming out every couple of years saying, no, what the guy said last time is wrong. What the previous people before that said last time is wrong. We need, our understanding is rapidly evolving. My challenge, especially for the young paleo scientists, is to come up with some novel ways to measure ice sheet hydrology and the past dynamics. Ice cores give us a single point record. They're extremely difficult to maintain. Some of those bedrock samples under the ice are some of the most expensive rocks on the planet. If you look at the dollars per kilogram of rock it took to get it. And yeah, what can we tell about Greenland's past hydrology, its past dynamics, its susceptibility to rapid collapse? Again, the ice core records get at that a little bit, but there's a lot more potentially if clever folks can figure out clever ways of doing this. I don't know that it's in my wheelhouse. I'm not enough of a paleo person to come up with these clever methods, but I'm hoping people in the room are. And then to work with the observational community, because our understanding of present day hydrology is still rapidly evolving. Greenland's changing fast, and we don't know how all that plays out in the next 100 years and or 1,000 years. With that, I will end it. I think I'm maybe just a few minutes over, but yeah, that's what I got.
All right, thanks. That was really interesting and maybe a little bit scary, but very cool overall if you get past all of that.
Yeah, same. I'm a dad as well, and that's terrifying, but yeah.
Yeah. So I will remind folks that you can send your questions, as Raymond's just mentioned, to Raymat in the chat, or raise your hand if you want to ask a question that way. We have a few questions that have already started coming in, so I'll go ahead and get started with those. So our first question, fairly straightforward, but I'll put it in the chat anyway. Are the fern layers geochemically distinct?
That's a great question. So in our 2013 traverse, so to start out with, I guess simple answer is yes. I mean, it depends what you mean by fern layers. Like obviously up in the dry snow zone, they can get annual records of accumulation from the stable isotopes in the fern layers, you know, from winter and summer snowfall. And so that's how they can tell annual records. And so those layers, but these melt layers it's a mix of, you've got surface meltwater melting and then refreezing at depth into previous fern that fell it was snowfall that fell at a different time. We took a whole bunch of isotope samples from the fern cores we drilled in 2013 when we were doing that. That whole radar traverse, trying to map out ice slabs across Greenland. And my colleague, Horst Maguth, took it back to the Geological Survey of Denmark and Greenland. They did take all the measurements. And as far as we could tell, it was basically a random number generator. Like it was a mess. And and in fact, this is an open invitation. If some better trained paleo folks want to look at that record of isotopes that we've got from where these ice slabs have formed, and see if you can make some sense of it, I would really welcome that, because we look at it, we go, I don't know what to make of this. It's all over the place. And which kind of makes sense when you get all these melt lenses from different periods of accumulation that have since melted and then at random depths have formed and then all amalgamate into a large ice slab. Like, you know, what sort of signature would you expect that to have? It's a mess. But I'm almost certain there's a very interesting story in there, or several, that could help interpret, for instance, past melt events from the ice sheet, from the deeper core records where there's melt events in there. But it's tough right now. So I don't know if that fully answers your question. So it's both yes and no, or yes and I'm not enough of an expert to make out the story. I've seen those records, those isotope records, and I'm just like, shit, I don't know what to make of this. So
maybe the most interesting answer you could have given, actually. Let's see. Another.
We still have that data sitting around, though. By the way, if anybody wants to like take a look at it, Horst hasn't done anything with it, so like it's there, it's measured. Might as well do something with it. Sorry, go ahead.
So another maybe. Oops. Fairly quick one. How large are the lakes that are starting to drain at the thicker parts of the ice sheet?
Bigger than the ones that are down low. So here's the thing. The lakes that form up high, and this is due to the ice dynamics. The thicker the ice is, the more it will mute out undulations in the bedrock. So if you get a rough bed, say a very rocky bed, if you got really thin ice, you only have 10 meters of ice there over really large boulders, you're going to see every boulder. You know, there's these huge undulations in the ice. And so the ice down low has far more undulations than the ice up high. The ice up high, the undulations are still there. If you stare at the horizon in the accumulation zone, which I've done many times, you can see there's a slight depression for a couple kilometers over there, and there's a slight rise for a couple kilometers over there. But the lakes tend to be larger, and they form from larger basins up high in the ice. The really small topography is muted out simply because the ice is 2 to 3 kilometers thick, and you only get the larger ice features like the canyons and other things that happens, which ends up meaning that on average lakes are larger up high. So when I say larger, like down low, you can get lakes as small as a few dozens of meters to maybe 1 to 500 meters wide. Up high, you can get them 2-3 kilometers, sometimes 5 kilometers across if you really fill them up big. they're larger lakes. And so when you drain those, unfortunately, that means you get a large amount of meltwater that's concentrating in these lakes. Yeah, I mean, I guess you didn't, yeah, I gave sort of a sideways answer to your question there on how large. I mean, on the order, it's anywhere from a kilometer to several kilometers wide, or, I mean, it can be small if you didn't fill it up much, but yeah, they're pretty large lakes. And when they hydrofracture, there's some videos out there of lake hydrofracture that are, I mean, you get these, like, they just suddenly drain in the span of 90 minutes. It's kind of incredible. You don't want to be real near it when it does that.
All right. I have sort of a follow-up question to that, kind of.
Yeah.
So this one says, when you end up with these major interior lakes, it must have a profound impact on the layers of ice that are formed. Do you have a sense of what that ice looks like in an ice core? How biased is the record we think of as perfectly annual ice core layers?
So that's a multi-part question there, and there's a lot in there. Yeah, it's a great question. So yeah, it certainly does have a profound impact on the layers of ice that are formed. Like I was saying, when we've taken isotope records from these ice slab areas where there's been multiple years of melt that have refrozen into these thick layers of ice, and then lakes on top of that. How that looks in an ice core, that's a great question. Again, the isotope records from these ice slabs are just a hot mess. We couldn't make out anything close to an annual layer in those, even though it was multiple years worth of snow and ice. And I suspect, and I mean, actually melt, I know for a fact that melt events, even small ones, just a few centimeters of ice that form, there are records in both Greenland and Antarctica of these sort of intermittent melt events that they can tell. They can tell it from the stratigraphy of the ice. The crystal structure of refrozen ice in firn is different than the crystal structure of simply faceted snow that has since condensed in dry conditions down into ice. They can tell from the crystal structure that this was a melt event, even when it's all been compressed down into ice. So they see those in the ice core records. They see them in Greenland. That's how they can tell that Greenland melted 160 years ago and before then in intermittent times, usually not 3 times in the last 10 years, but that's what a changing climate does. Anyway, I'm getting off track. How biased is the record we think of perfectly annual ice core layers? So, I mean, the ice cores get harder to date annually the deeper you go. For obvious reasons, the layers getting squished together, especially when you get down near bedrock. There's a lot of weird dynamics. You can actually get folding in the ice layers and things like that. It can make it hard to interpret. And so, down deep, they spot check the records, the dating they have with things like ash layers from volcanic eruptions. If we know of, a volcano that exploded in Iceland in the year approximately 1215, I'm just making this up, by the way, I don't know this, but then you can see that ash layer across Greenland, and they get these ash layers across Antarctica. They can get geologic records of when these volcanoes went off, and they can test the chemical signatures of every one of these layers of ash and tell exactly which volcano it came from. And so you can, from the ash layers, tell when certain segments conclusively formed. And then you can sort of interpret between that. It's not a perfect annual record like in Antarctica when you see these records of the last 800,000 years. They don't have every single year. They can't tell you the difference between year, 799,000 and 799,001 BC. As for how biased, that's a slightly different question than how confused. That's a great question. There's some work being done on, for instance, when you melt the surface, some of it evaporates, and you're going to get some isotopic signature in snow that's evaporated from liquid. You're going to get lighter isotopes evaporate away preferentially than heavier isotopes, which will then bias your record a little bit about what's left over. You'll get your heavy isotopes left over, and that can bias it slightly. That's usually part of why they always try and drill cores as high in the ice sheet as possible. In the area where there's as little melt record as possible, they don't tend to drill cores down at CanU where there's a bunch of melt every year. It's just the core's a mess. Like, why would they do that? It's go up where we can read it cleanly up at Summit. I mean, it's a multi-part question. I don't know if I quite got to it, but when you start getting to these really thick layers of ice, it really does confuse the record. And it makes it hard to read. Again, there's probably really interesting stories there, and there are people that do try and tell them. But as for like these thick ice slabs, like, great question.
Yeah, I agree. Very interesting. So our next question is, are Indigenous communities involved in your research?
So in the past, not much, I'll fully admit. The research is funded by NASA, most of it we did, and some by the NSF. We have, in more recent years, involved and greater involvement. We've got a new grant out of the University of Colorado here. It's directly working with ASIAC. That's the Greenlandic Geological Survey. It's sort of the Greenland's version of the USGS. That is more directly participating in this work. But Greenland, I mean, it's something that I've got to fully admit that most US funded science is very colonial in nature. You fly in on a military plane, do your science, and leave. And that's something that I do very much think needs to change. It's really problematic in a lot of ways. And so getting the Greenlandic community and the Greenland scientists, and in fact, there are Greenlandic scientists, ASIAC houses them, and involved directly in all of this research is really important. So
that's great that you can start to work with the group. I think right now this is our last question. So if you've got anything else, please get it in. But just another one, how does a melt lens form?
Yeah. So it's snow hydrology is kind of weird. And there's a lot of people that study snow hydrology, a lot of it mountain snowpack, where we get fresh water sources from here in Colorado. But snow's weird. It's so there's hydrologic pathways. What they show is that when you get just a tiny little melt, like a couple of millimeters of melt, it sort of just is this little homogeneous layer. It sort of trickles down a little bit into the snow and then refreezes, and you get this just kind of homogeneous layer. But when you start to get more melt, it finds what they call preferential flow paths, where you get these pipes. The water will funnel into this sort of weakness spot in the fern and then trickle down through a column. And we've dug out in snow pits these columns. We drilled them up in cores. We've got a core samples with columns of ice straight through them, with fern around it. That it will go down meters into the snow, but then hit a hydrologic barrier. There's a lot of the difference in the faceting and density of layers of snow and fern, and hoarfrost layers and other things that form in snowpack over time will then cause these sort of differences in permeability among different layers in the fern. And so it can hit sort of a hydrologic barrier, not a complete one. It's still fern, but it's more porous here than it is there. And once it does that, it spreads out. You actually get this lens that spreads out over anywhere from, just a few centimeters to meters wide of these individual little lenses that can form in one melt season. And of course, once you've got a lens there, then if water hits that again, it can sort of freeze to the top of it as it spreads out. It's a large hydrologic barrier. So you go over time, form these really thick ice lenses, which then eventually form into these kilometers wide ice slabs that we were seeing in Greenland. But it's really the hydrology of the snow in fern. And keep in mind, the fern layer is usually pretty cold. Even if it's melting at the surface, oftentimes it'll be -15, -20, -30 degrees Celsius at depth. And so really the water is sort of trying to get hydrologically and from gravity, just trying to get as deep as it can before it's overcome by the cold content in the fern and freezes where it gets. So the more meltwater you get, usually the deeper you can get it. You can get percolation down below 10 meters depth, 30 feet or more, but before it forms one of these lenses. But it's got to be quite a lot of water to overcome the cold content of the fern. But yeah, when it hits a hydrologic barrier or starts to freeze, it can form a lens.
All right. Well, I think I don't see any new questions. So with that, I will go ahead and take back over the screen share.
Awesome.
And thank you so much. I've learned a ton from your talk. It was very interesting. So, okay. Sorry, my computer's being a little bit slow, but I think everything is up now. So thank you, Mike, again for your talk, and thank you everyone else for joining us and listening in. We'll drop the weekly feedback form link back into the chat in case you want to take a chance to do that. And please come back next week to hear Anja Frink from the University of Hamburg in Germany talk about marine redox fluctuations during the Ediacaran-Cambrian transition, insights from chromium isotopes. And so with that, we'll have tea time with Mike, who's agreed to stick around, which is just an informal conversation where we'll all unmute and say hi and just chat about whatever comes up. Whoops, so we had two behind the scenes peek. We had two questions, and this was the second one. I've forgotten to delete the word alternatively. But our question of the week, keeping with our ice theme, what's your favorite icebreaker question? So with that, we'll have a quick 2-minute break. So you can get up and stretch your legs, grab a drink of water, come back in 2 minutes with any paleo pets if you want.
I'm going to leave for a couple of minutes and come back as well. So yeah.
Yep. All right. So I'll just start this little timer and we'll see you all in a few minutes.